Hello, everybody. Welcome to the Neo4j online meetup. So today we're going to be, so I'm joined by Thomas.
Yeah, that's my English name. My English name is Thomas, but my real name is Tomaž.
Oh, I got no. I think I'm going to struggle to pronounce that one correctly.
I mean, it's not problem. It's just you just do homage, but with a T, so it's Tomaž.
Tomaž. I have to practice a bit more. So we're going to be looking at some algorithms that were recently added to the Neo4j graph algorithms library. So these are similarity algorithms. And so I guess before we get started with that, Thomas is going to be showing some code from some blog posts that he's written. So for that section of the talk, it'd be useful to make sure that you have your resolution of the YouTube video quite high. So set it in the bottom right-hand corner on the little cog. Set that to at least 720p, and that should be good enough for you to see all the code. Apart from that, we've got the live chat, obviously, on the right-hand side. So if you have any questions that you want to ask when you're watching live, you can post them on there. And if you've got any questions afterwards, we'll create a Neo4j community forum page for you to ask those questions. So Thomas has been a member of the Neo4j community for a while, but in case you haven't come across him so far, maybe you can quickly introduce yourself and tell everybody how you got into Neo4j in the first place.
So basically, I've ran into Neo4j around 2.5 years ago, and I really loved how the community helped. At that time, it was only Slack. Now it's also Discord, and I really loved how people are really helpful, trying to help you. So I wanted to give something back. So then I started to help out as well. And then I met Michael, obviously, for those.
Yeah, the center of the graph.
Yeah, I guess everybody knows Michael. So we kind of decided to start collaborating, and basically my task was like that. It's like I was learning everything by myself. So my task was basically to write a blog post about everything that I learned, which is really nice also for me, because like I can copy paste a bunch of stuff and don't have to memorize everything. And then I don't know, about a year ago, the graph algorithms library was started to be worked on, and I really liked graph algorithms and decided to help with the documentation and tutorials, and basically just showing how easy it is to do it. And you don't need to, because I'm not a math wizard, and you don't really have to be like a math wizard in order for you to do all sorts of awesome analysis with the graph algorithms.
Yes, I think you've probably written the most content related to that library. And there obviously, you've written about all different types of things that you can do with it. But as we mentioned at the beginning, today we want to look at the similarity algorithm. So I think we added those middle of September or something, something like that. But wanting to run similarity computation on a graphs or on graph data is not like a super new thing. So when Thomas and I were talking about this just before we started, we actually found this is something that people have been doing for quite a while. Like a number of years ago, the first attempt to do this was on a movies graph, so trying to work out the cosine similarity of people based on their common movie reviews. So I guess maybe Thomas, now you can present on your screen, and then we can.
So basically, okay, I'll just do like a quick overview. Oh, can you see my screen?
Yep.
Okay, so basically, there were 4 similarity algorithms added. First is the Jaccard, cosine, Euclidean, and overlap similarity. And the cosine and Euclidean distance are based in Euclidean space, so you require like a feature vector, and the Jagged and overlap similarity require a category vector, but we'll get to that real soon. So basically, when we were looking how we should start this, we found that there were like a couple of different cosine similarities implemented. So like, because this is something that's been calculated for ages, so maybe not ages, but yes. So like we found this graph gist that was like the first version of the cosine similarity in Neo4j, and it's using only ciphered. Just so in case you don't know what the similarity is, the cosine similarity, so I guess, but you would need to be a math wizard to understand this. But basically, the cosine similarity ranges between -1 and 1, and like if it's 1, they're perfectly similar, and if it's -1, they're perfectly dissimilar. But just to give you like a hint how it was first used, so this is like the query written in only cipher, how to do it. And that's been like how people did it for quite some time. Then when APOC got, like the second stage was when the cosine similarity was integrated in APOC, and that's basically in my first graph algorithms blog post, where I did it on the movies database that you can easily reach by just typing play movies. So what I did was just took like 2 dummy features, which was the age of the person and the how many movies this person acted in or directed, as 2 features. So it's like a really dummy showcase how to use it. As with features, like you got to normalize it. I mean, you don't have to, but usually you normalize features so that they are the, how do you say, the influence are the same, so that one feature doesn't influence the whole thing. And if you can see it here, really, let me see if I know how to do it. Okay, so this was like the APOC algo cosine similarity integration, where you just basically put in 2 arrays of features, and it calculated the cosine similarity for you, and then basically you can do whatever you want. Usually we store it like in a new graph and create a similarity network between our nodes. So that was like the APOC version of cosine similarity. And now, like for 2 months now, since it was introduced in September, we've got the cosine similarity. Okay, no, that's the wrong one. We got cosine similarity also in algorithms library, and that's, as it is the newest, it's also the best one and the easiest one to use. So what you do now with the cosine similarity is basically you provide an item, which is in our case, for example, a node, and you provide a feature vector of that node, and just put it into the similarity algorithm, and it does all the things you need to do, and you can write it or stream it back depending on what do you want to do with it.
Yeah, so maybe I can explain a little bit how this works as well. So what we're doing, so this, as Thomas said, so this relies on having numbers. So in this case, we are using node IDs in there. So that's what the ID function on the second line of the query does. And then the value that you pass to weights needs to be the same size vector for each, like effectively the same size array for each of those items. And then what it's doing when you call algo similarity cosine is it's in parallel, kind of going and working out the overlap of all the things that are in that user data collection. And then in this version, the one that's on the screen right now, see it doesn't have, it goes algo similarity cosine. So this one's actually storing the results in the database because we have that right flag set to true.
Okay.
If we put a stream, it will give you back the pairs, right, instead. Yeah, and then by default, it creates a relationship type called, I think we called it similar, between the nodes. And it's only, in this example, only creating that relationship if the similarity between two nodes is greater than 0.8. So it's 0.8 on that scale that Tomaž described, of -1 to 1.
So basically, like, as you can see it also on the screen, the cosine similarity is like effectively like 80 or 90% of the K99 classifier algorithm. So basically it finds similar nodes in our graph, but then like with the classifier, you would just say, okay, our new node has the majority class of the K nearest neighbors. Actually, we don't do that in this algorithm, but like you can do it like in step 2 if you wanted to. But the thing is, basically, it calculates cosine similarity between all of pairs of nodes. So having it written like this as a procedure and doing this parallel helps really big. Because like I was really surprised, like, because I remember like a year ago or even more, I had a use case when I had to use the cipher, just plain cipher, and it took a while because it has to calculate distance between each pair. So if you got a big graph, it takes some time, and like that that became a little better with APOC implementation, and now with the algorithm implementation, it's much better. So that's really awesome. And like you were saying, for the similarity cutoff, it's basically like you never, because like if you're searching for similar nodes, you don't want to store the relationships between not similar nodes, because then you basically get a complete graph. Because like if you would just leave the similarity cutoff at -1, which is the perfect dissimilar value for cosine, then you would basically just connect every node, every pair of nodes in the graph, and that's really not cool. So and if you want to do like community detection after you infer the new similarity graph, they won't really work, because community detections as of now, like the Louvain and label propagation, don't really work well in a dense network, because like if all of the nodes are connected, then it's basically just one giant community. So you definitely you always want to use either similarity cutoff, or you can just use the top K parameter. We just say, okay, just store the relationship to top 5 similar nodes, and that's basically it. But yeah, keep in mind, you never want to, at least in theory, store the relationship between dissimilar nodes, because then you get a complete graph. And if you're doing community detection like I was doing here, then the community detection will just return one big community, and that's basically worthless if you want to find some communities within our graph. So as you can see, like over time, the cosine similarity progressed a lot, and I'm guessing this is the final and best version, and I doubt there will be a better one.
The only other thing that we're currently adding to that is that if you have like quite sparse embeddings, so like imagine that you were trying to work out the similarity of people based on the movie ratings. If you take that one and imagine there are loads of movies, right now you have to build an array which has a lot of 0 values in to get it to do the computation properly. So we're working on we have like in progress a version where you can do this, the first 3 lines of this query that you have on the screen right now with the cipher projection instead. So you can just say, this is the node that I want to compute similarity, and and then this is the relationship or relationships that I want you to take into account to find the things that you should aggregate that count as my weights. So that's the only change that we're planning to do.
But I guess that will be that users won't really see. They will see performance difference, but they will just still call algo similarity cosine.
Yeah. So and you pass in a graph cipher on the end as the parameter is the plan. The only other thing which is quite useful with this procedure is that if you don't know what to set your similarity cutoff to, you can set that the right value to false, and there are a bunch of other parameters that come back which will tell you the percentile of similarity at different percentiles. So it gives you like the 95 percentile, the 99 percentile, the 75 percentile, and so on. And so you can figure out like where should I set it so that I get, as Tomaž said, I don't want to get too many nodes connected to each other. So I want to check that similarity pairs is not too big, but equally we don't want it so low that very few things are connected. Otherwise it's not helpful either. You want it somewhere sort of in between.
Yeah, and there's not like a rule one fits all. It's basically just try it out, see what comes out, and then tweak it that you get out as sensible information out of it as possible, basically. So that's that about cosine, and we also wanted to do a demo on the Jagged index. So here we had like a feature vector, maybe just to show you real quickly just what does that mean. So for example, we've got a movies graph where a person can rate movies. So for example, we've got Michael Sherman and Michael Hunger, which is obviously everywhere. And they both rated some movies. So for example, this can be really useful in a recommendation system where you want to recommend movies that similar people that like you found interesting. So as you can see, here like a list of a few movies, and each person like gave them the rating. So what we do is just create a feature vector for both of them, and then just calculate cosine similarity, and that's that. Quite simple. And you don't have to worry about all the math underneath it and the parallel stuff as well. So that's that. And now if we move on to the Jagged index, which I have right here. So I found this nice picture that I stole from somewhere, but and it's basically the definition of Jagged index is intersection divided by union. So if you can see here, like a person in intersection of person A and person B is like an apple, strawberry, and a lemon, and they all got some other fruits that are not in common. So basically, it just takes the 3 fruits, which is the intersection, and divide it by all the possible fruit, and that's how you get an intersection. And so you can see that here we're not in a Euclidean space because we don't use feature vectors, but we use so-called category vectors. We just mean like an app. We just like assign a number. So like an apple would be 1, strawberry would be 2, lemon would be 3, and then we just find intersections and unions. That's that. So we can show you how to use it. I'll basically just copy and paste.
So maybe you can just quickly explain the data set before you show it.
Okay, yeah. So basically the data set is from the Kaggle. It's a list of 15,000 electronic products. And it's got, for me, but the interesting part was, so we've got a bunch of products that can have one or many categories. And basically I wanted to find the most similar categories, because like it was like when I wrote it, it was a bit counterintuitive. Even if you can say, if you, okay, let me put it in Neo4j and then explain it. So if you can see, then basically we just say, okay, match all the products that are part of the category. But then I say, I want to find similar categories and not similar products. And I put the ID of the category at key item, and then put the IDs of the product to categories, which might be a bit counterintuitive. I mean, if I wanted, but then I realized that like after I finished this, so I didn't want to change it. But like basically, we could turn it around and just say, okay, but now, like here we're finding similar categories based on how many common products they have. But like if I just wanted to turn it around and say, okay, now find me similar products based on how many common categories they got, I would just turn it around. And basically that's it, voila. I've just created a different query. So in the first case, I was searching for similar categories, and now in the second case, I'm searching for similar products. The thing is just like, because the second parameter is named categories, so it might be a little counterintuitive if I turn it around, but I mean, for most of you, that shouldn't be a problem. So basically what we do is just say, okay, find all the categories of the product, or basically find all the products of the category and create a JCat index on them. So there's that. And as always, we want to use similarity cutoff because we don't want to have a really dense graph, because then, like most in my use cases, I used the community detection at the second step. So that's definitely, you want to avoid dense graphs with similarity cutoff.
What's the range of values you get for this one?
What do you mean? I think it's from 0 to 1.
Okay, so cosine was -1 to 1, and this one is 0, I mean, meaning not similar. 1 is completely the same.
Yes, because I think only cosine has the values spanned between -1 and 1. JCat and overlap similarity are between 0 and 1, and Euclidean is basically between 0 and infinity. But it goes the other way around, whereas in Euclidean distance, the less is better and the more is worse. But yes, okay, let's run the algorithm. And just like as Mark was saying, like if you don't really know which value to use for similarity cutoff, you can just type in 1 and just see what happens. So, I mean, and just look at the percentiles and see what's going on. It's a little bit funny.
Yeah, it's using the HDR histogram to keep track of those numbers, and somehow sometimes when it's 1, it gives you this odd. I think it's like I'm not sure exactly how does it come up with the computation. I think it's more a bit of an approximation, but yeah, there it just means that there's half the, so it's computing the histogram, but including your cutoff. So it's only counting items which are above the cutoff. So in this case, it's saying of the items above the cutoff, 75% of them are the same, right? Same. So less, the top 25% are exactly the same.
Yeah, I mean the top 50 because the.
Oh, sorry, yeah. Sorry, I didn't spot that.
Yeah, so basically we've got a lot of categories that are the same. So like, and now if we wanted to check, like, let's find, I always cheat, but let's find like the two, or like a bunch of most similar categories. I'll just put the notes here just to be really nice, and then just do A, B, and what does it use to say? Okay, it uses code. Okay, so similarity, and then ordered by similarity descending, and let's just look at the top 10. For example,
so if I remember right, the similar relationship is actually, because this is a symmetrical algorithm, I think you're able to look at it either way. Like,
yeah, and I think we only store like one way anyway, because
so the way we do it is when it's computing the similarities, it doesn't compare all the nodes against all the values against each other. It compares like them sort of half. So it doesn't go A and instead of going, I'm going to compare A to B and B to A, it skips half of
it. Because like even if you look at this picture, like it doesn't matter of the direction, because like the union and the intersection will always be the same regardless of the direction. So
so I think I think that's the same for cosine and Euclidean, but for overlap, that has the direction and is important. So the first node that you see, or the first value, is the smaller one. In that case, it actually has some meaning, but for the other three, there's no meaning.
Yes. So basically, we can see that pet supplies technology is really similar, or like basically the same as dog. It's funny, like you've got a pet cameras category, but I guess that's a thing now. And like even if you check like pet supplies and technology, and you've got surveillance, security, and pet cameras. So I haven't really checked that out, and it's really funny. And even here you've got wearable pet cameras. So I guess people like to put cameras on their dogs and surveil them from anywhere they are. I don't have a dog, so I don't really relate to that, but that's funny. So, and now we just looked at some categories that are basically the same, because if you check the similarity is 1.0, that means basically that the intersection is the same as the union. So basically all of the products that the pet supplies and technology has is also under category dog. And I guess they sell cameras a lot. But this is like just checking one-on-one, but like now maybe if we want to find communities of similar, but basically,
yeah, I guess like another thing you could do with just the similarities before we go to the next bit is if you were showing like on a website, like the person was in this category, you could say, hey, other similar categories are these ones here.
Yeah. So basically some sort of recommendation system.
Yeah, very obviously very simple one. But
but yeah, it's a start. But then maybe you can, because like you can start with that and add a couple of rules.
Yeah, you probably need a few more rules, because otherwise someone's coming in there looking for some pet supplies and they end up with surveillance equipment, which might be not quite what they expected.
Yeah, but I guess there's basically the data set problem.
Yeah,
yeah.
So that's it's kind of a thing, isn't it? With all these, with these algorithms, they only will find you the similarities based on what data you have. So the more data you have, the more accurate the similarities it'll find.
So basically, if we check, actually it means electronic products and pricing. So basically, it does make sense because they're just selling, or basically this data set contains only electronic devices. So it makes sense that there are a lot of cameras and video equipment in there. Okay, cool. And now, because now we're just checking one-on-one, but then if we wanted to find communities of similar categories, we can use label propagation or Louvain. I basically don't really have any. I'm not either for label propagation or Louvain. Basically, as I found out in my blog post, they usually perform quite similar. And basically, it really depends on you what do you want to use. And like here in this example, I used label propagation. So what I said is, okay, load all the category nodes and load all the similar relationship between them, which we got from the jQuery index. And basically return communities of those categories and only top 10. So if you run this, what did I do?
Two queries together, are there? Maybe while you're fixing that, I can quickly do a crash course in what label propagation is doing. So the label propagation algorithm is based on the idea. So everybody starts with what we call their own label. So and it's based on the node ID. So the label that you see that comes at the end is one of the node IDs that we had there. And it's on each iteration of the algorithm, a node will ask its neighbors to vote for what they think its label should be. So the neighbors are trying to kind of get each node to come to their label. And so ask all its neighbors, hey, what should be my label? And then at the end, it'll check, okay, what do my neighbors think my label should be? And if it's different than what they have now, then they will go to the majority label choice. Then if it's the same, then they didn't do anything. And you can kind of control how many iterations that runs for. So if you just did it for one iteration, you probably get quite a lot of different labels. But if you run it for multiple iterations, it tends to group things together into communities, like what Thomas has done. And now I see it's worked.
Yeah. Basically, before that, I said that label propagation and Louvain are basically the same. I forgot that a month or two ago, we added a hierarchical option for Louvain. So basically, as you said, for label propagation does a bunch of iterations, and so does Louvain. But with Louvain, we can check each intermediate iteration. So I've also written a blog post about that. And it's basically with Louvain, and each iteration, it starts with small communities, and then after each iterations, community get bigger. So that's also a really nice thing to do, if you want to find some hierarchical communities or really small communities, because label propagation, if you got a big graph, it will return big communities, but it will never return you. I mean, basically it could, because if you could just define max iterations and go from one. But yeah, domains got that option as well, which is really cool. So okay, now that I fixed the level propagation, like we can check some of the similar categories that our algorithm found, and like let's look at here, for example, I found a bunch of GoPros. So we've got basically a category that's like a community of categories that's basically a GoPro accessories. So we've got hand and celeb grips, accessories, camera accessories, cam mounts, chest supports, and okay, actually the camera, and then just a bunch of accessories as well. And if you see, we found like a community of similar categories. So this is basically a very simple example, and you could do lots of different things with that. But just to show you like how easy it was to like infer a new similarity graph with Jacob index and then find communities on that new similarity graph. And yeah, because I think, yeah, but like if you check, we get like really nice results, but I think that's just because of the data set, because if you check, there are a bunch of categories that are really the same. And if when we're checking those similar categories, we can see that, yeah, they really fit nicely together. You don't have to be like a genius to say that basically all the GoPro and camera accessories go together. So here it basically just says GoPro is another camera, and here's a bunch of accessories that are available. So that's that for the live demo. I'm guessing, are there any questions? I know that that's your department, Mark.
Yeah, I'm just checking.
Like in the meantime, what I could do is like before I showed you how easy it would be to just turn around and find similar products. So maybe we can do that as well.
Yeah, the only other thing I was thinking was for the last example you showed, you could, in theory, like compute the similarities between those products using a cipher projection with the graph algorithm procedure. And you, in theory, you could do that, and you could just compute the Jacquard's score in cipher exactly as we did in the first example. The reason that we want to use the procedure is because it's much faster, and it's much faster because basically we're running it on multiple cores, whereas the cipher queries are all running on like one thread to begin with.
And basically, I'm not sure if it's possible, but I guess it is, because like I was thinking what we could also do is just basically nest these procedures, and because like lots of people don't want the data stored, or like because like if you play around with different similarities and trying to find out what kind of communities comes out, maybe you could just use the streaming similarity algorithm and just and nest that into the community detection, so you can do it all in one go without saving any intermediate results, and basically keeping your graph tidy, because like lots of people like their graph tidy, especially
sounds like you've talked yourself into another blog post.
Yeah, that could be also.
The only question we have at the latest question we have is, which maybe we can answer together. So, is label propagation analogous to clustering? Is there any threshold parameter we can add to determine the number of nodes that are under a particular label? So, yes, label propagation is a type of clustering. So the term clustering and what in the Neo4j graph algorithms library we're calling community detection are kind of doing the same things. So they're at a high level working out which nodes are similar to each other. And then you have different ways of determining that similarity. So the one Thomas has just been showing is similarity based on voting of your neighbors on a similarity graph that we computed based on the Jacquard computation. If you ran that on a different similarity graph, perhaps with a different similarity cutoff, maybe you see a different result.
And it doesn't even have to be a similarity network. You just have to have
that's true.
a direct network between nodes, and basically, because you can also let's find dissimilar groups or something. It doesn't have to do anything with similarity. So, because imagine like a network of friends, and just say, okay, find me different communities of friends, and that's it. And you don't, and that's quite easy to do with the new graph algorithms.
Cool. So I've put some links to your blog post, or Tomas's blog posts, on the chat. So if you want to, you probably need to set aside a bit of time. So if you want to read the whole lot, there are.
Yeah, I mean, like as I mentioned before, like everything that I learned about Neo4j, I put it into blog posts. And as you'll see, I learned a lot about Neo4j. So there are like, I don't know, like 30 or 40 blog posts I did, like in only this year. So there's a lot of content for you to go through.
Cool. All right. I guess we can probably wrap up there. So if you, I hope you enjoyed Tomas's presentation. If you did enjoy the talk, don't forget to like it on the YouTube video, our shameless self-promotion, to make sure that other people can find the video. And maybe we'll see you again next week. So we'll be back on Thursday again next week, and we have Ward Cunningham, so from the Agile Manifesto, one of the original authors of the Agile Manifesto, is going to be presenting a project that he's been building with Neo4j. So that'll be on next Thursday, so the 29th of November, at same time as we did today. So 5 p.m. if you're in the UK, 9 a.m. West Coast. So I hope you can join us for that one. And I guess happy Thanksgiving to the Americans amongst us. But Tomas and I will still be working tomorrow, so we don't know what to do. Cool. So thanks again, Tomas, and thank you to everybody for joining. We'll see you on the next one.
Okay. Bye.